Dear students, Assalamu alaikum. Today we are going to recapitulate the last lecture where we have discussed properties of magnetic lines of force. This is class for class 12th, and as you know that yesterday I told you about magnetic lines of force, how we draw them. So what was the definition of the magnetic line of force? It was that the path along which a magnetic needle or a compass needle will follow in a magnetic field is called a magnetic line of force. If we have a magnetic field anywhere in the region and we move the magnetic needle in the region, then the path followed by the magnetic needle or the compass needle will form a magnetic line of force. So there are some properties of magnetic lines of force, and the first property is that magnetic lines of force are hypothetical and do not exist actually. That is, they are hypothetical in nature. Number two, magnetic lines of force are continuous closed curves extending throughout the body of the magnet. Unlike electric lines of force, electric lines of force are not continuous, they are discontinuous. They originate from the positive charge and terminate on the negative charge. But magnetic lines of force are continuous, they are not discontinuous. They do not originate from anywhere, they do not terminate on anywhere. So they pass through the body of the magnet. The third property is if we draw a tangent to the magnetic line of force, we will get it will give us the direction of the magnetic field at that point. For example, if we draw uh, a tangent here, so this will be the direction of magnetic force here. This will give us the direction of the magnetic force. Similarly, if we draw a tangent here, you will again see that the this line will give us the direction of the magnetic field below the magnet. So the tangent drawn to the magnetic line of force gives us the direction of the magnetic field at that point. Similarly, outside the body of the magnet, the direction of the magnetic line of force, as you can see from the picture above, is from north pole to south pole, and inside the magnet it is from south to north. The direction of magnetic line of force outside the magnet is from north to south, and inside the magnet is from south to north. Then there is another property: no two magnetic lines of force will ever intersect each other. For example, if they intersect, then the magnetic field will have two directions at that point, which is not possible. If anybody asks why they are not intersecting anywhere. If they intersect, then the magnetic field will have two directions, which is not possible. So the two magnetic lines of force will not intersect each other. Then there is seventh one, that sixth one. The magnetic lines of force contract longitudinally and dilate laterally. Longitudinal means at the poles, south pole and north pole, they contract. They come closer to each other, and at the in the middle of the magnet, you will see that they dilate. They move away from each other. Then the seventh one is magnetic field is stronger where the lines are dense. That is at poles. At poles, the magnetic field is stronger than the magnetic field at other places. Now let us discuss what is magnetic dipole. As we have already discussed about electric dipole is constituted by two equal and opposite charges uh, separated by a small distance, vector distance in space. Similarly, we know that if we separate the two charges, we can get single poles. But in magnetic dipole, we cannot get a single pole. So magnetic dipole consists of two unlike poles, that is north pole and south pole of equal strength. The strength of north pole is equal to the strength of the south pole, and they are separated by a small distance. Here we denote that small distance by 2L, whereas in electric dipole we denote that small distance by 2Q, 2E. For example, a bar magnet forms a magnetic dipole. A compass needle is the example of a magnetic dipole. Similarly, uh, a dip needle or horseshoe magnet. There are so many examples which form a magnetic dipole. So what is magnetic dipole? It consists of two poles of equal strength separated by a small distance. Now, what is magnetic dipole moment? The product of the pole strength M and the small distance 2L between the poles is called magnetic dipole moment, and it is denoted by M, capital M. M is equal to M into 2L. If we multiply the strength of the magnetic dipole with the distance between the two poles, we get a magnetic dipole moment. It is just like as in electric dipole. When we multiply one of the charges, remember that, with the distance between the two charges, we get an electric dipole moment. So here it is magnetic dipole moment. Electric dipole moment M is equal to Q into 2A, and here magnetic dipole moment is equal to M into 2L. Magnetic dipole moment M is a vector whose magnitude is equal to the product of the magnitudes of M and 2L, and whose direction is from south to north. Remember this thing, from south pole to north pole. The SI unit of magnetic dipole moment M is joule per Tesla. Joule per Tesla, or ampere meter, or uh, uh, ampere meter square meter. Ampere per square meter. Actually, it is ampere meter square. It is not ampere per meter square. It is ampere meter square. So magnetic field intensity on the axis of a bar magnet. Oh. Consider a bar magnet north-south of magnetic strength M and of magnetic length 2L. Let M is the magnetic moment and O be the center of the bar magnet as shown in figure. As you can see in the figure, we have to find the magnetic field on the axial line of the bar magnet. Axial line, the line which passes through the axis of the bar magnet, is called axial line. So you can choose any point on the left side of the bar magnet, on the right side, as I have chosen on the right side of the bar magnet, point P. And we have to find the magnitude of the magnetic field at point P. So let us consider a point P at a distance r from the center O. At a distance r from the center O on the axial line of the bar magnet. According to Coulomb's law of magnetism, the magnitude of the magnetic force Fm is given by Fm is equal to mu naught upon 4 pi m naught upon r square. What is m naught? We place a tiny magnet at point P, say compass needle, and here this m naught, it is the strength of the pole of the compass needle. We place a compass needle at point P. The strength of each pole of compass needle will be denoted by m naught. Remember this thing. M is the strength of north or south pole of the bar magnet, whereas m naught is the strength of the compass needle which we place at point P. So then we apply Coulomb's law of magnetism. Just as you know that Coulomb's law in electrostatics, E is equal to 1 upon 4 pi epsilon naught. Instead of 1 upon 4 pi epsilon naught, we have mu upon 4 pi here. Remember this thing. Epsilon naught is the electrical permittivity of free space. Here mu naught is the electrical permeability of free space. There it is permittivity and here it is permeability. So by analog of Coulomb's law, the Coulomb's law in magnetism is given by Fm is equal to mu naught upon 4 pi m naught upon r square, where r is the distance between the centers of the two magnets. So as you know the definition of electric field E, that is equal to F upon Q naught. So by analog again, the definition of magnetic field B is given by Fm. B is equal to, B is the magnitude of the magnetic field. B is equal to Fm upon m naught. As you know in electrostatics, electric field E is equal to Fe upon Q naught, and here by analog magnetic field B is equal to Fm upon m naught, where Fm is the magnetic force. There F is the electric force. Fm is the magnetic force. So this implies B is equal to Fm into 1 upon m naught, which implies B is equal to mu naught upon 4 pi m naught upon r square into 1 upon m naught. M naught and m naught will cancel. This will give us B is equal to mu naught upon 4 pi m upon r square. So we have to use this relation. Remember this thing. We have to use this relation to find the magnetic field on the axis of a bar magnet. The magnetic field now there are two fields at point P. One field is magnetic field is B1 due to north pole and the other is due to south pole of the bar magnet. The magnetic field B1 at point P due to the north pole of bar magnet. Due to the north pole of bar magnet is given by using the above equation. It will be B1 is equal to mu naught upon 4 pi m upon uh, n p square. The distance between north pole and n and p. The distance between n and p. So due to north pole of bar magnet and by using the above relation B is equal to mu naught upon 4 pi m upon r square, then we use that relation, we get B1. That is the magnetic field at point P due to north pole of bar magnet. B1 will be equal to mu upon 4 pi m upon np square, which gives us so we will get B1 will be equal to mu naught upon 4 pi m upon r minus l the whole square. Now let us denote this equation by 1. Now what is the direction of B1? B1 is directed along NP produced. It will be from north pole N to point P towards point P. Similarly, the magnetic field B2 at point P due to the south pole of bar magnet is given by B2 is equal to mu naught upon 4 pi m upon SP whole square. This implies B2 is equal to mu naught upon 4 pi m upon SO plus OP का whole square. Square of SO plus OP. This gives B2 is equal to mu naught upon 4 pi m upon L plus R whole square. Let us denote this equation by 2. B2 is directed along PS, means its direction will be from south pole of the compass needle, so sorry, from south pole of the north pole of the compass needle towards the south pole of the bar magnet. That it will be from P point P to S. So B1 and B2 are in opposite direction. Since B1 and B2 are in opposite direction, and B1 is greater than B2 because north pole bar magnet is close to point P, so B1 will be greater than, its magnitude will be greater than B2. Therefore, the net magnetic field intensity B at point P is given by B is equal to B1 minus B2. Now, when you substitute the value of B1 and B2, you can see from here, from this figure, you will ultimately find that B will be equal to mu naught upon 4 pi m upon r minus L whole square minus mu naught upon 4 pi m upon L plus r whole square. So we can take common mu naught m upon 4 pi. It will be 1 upon r minus L whole square minus 1 upon r plus L whole square. This will give us B is equal to mu naught m upon 4 pi r plus, when we cross multiply them, r plus L whole square minus r minus L whole square whole divided by r minus L whole square into r plus L whole square. This will give us mu naught m upon 4 pi r square plus L square plus 2rl minus r square plus L square minus 2rl divided by r square minus L square whole square. When powers are same, bases are multiplied. So we have used that formula here. So it will be r square minus L square whole square. This gives us B is equal to mu naught m upon 4 pi r square plus L square plus 2rl minus r square minus L square plus 2rl divided by r square minus L square whole square. So the similar terms will cancel out there. R square will cancel with R square, L square will cancel with R square. So ultimately we will get 4RL. B is equal to mu naught M upon 4 pi 4L divided by R square minus L square whole square. So this gives us mu naught upon 4 pi M we take inside the brackets and we multiply it M into 2L into 2R divided by R square minus L square whole square. Now this will be equal, B will be equal to mu naught upon 4 pi R square minus L square whole square into M into 2R, because capital M is equal to M into 2L. So M into 2L will be equal to capital M. Small m into 2L will be equal to capital M. That is magnetic moment of the bar magnet. So this will ultimately give us B is equal to mu naught M R upon 2 pi R square minus L square whole square. Now if R is very large than L, that is the point P is very far away from the magnet. Then the length, that is the distance between the two poles of the magnet, will be neglected. That's L can be neglected as compared to if R is very large. That's point P is very far away from the bar magnet. Then B will be equal to mu naught M R upon 2 pi R square whole square, because L we neglected. So L will be equal to 0, L square will be equal to 0. This equal as B is equal to mu naught M R upon 2 pi R raised to power 4. This gives B is equal to mu naught M upon 2 pi R cube. R and R will, 1 R and R will cancel. Now since B1 is greater than B2, the resultant magnetic field B is directed along B1, that is along MP. Now let us take the equatorial line. Let's take the equatorial line. So what is equatorial line? The perpendicular bisector of a magnetic dipole is called the equatorial line. So we have to take the equatorial line and find the magnetic field, magnitude of the magnetic field on the magnetic field. So let us consider again a dipole of rectangle small m separated by a small distance to L. Then we take the equatorial line, that is the line which bisects the dipole, and we take a point P on it, as you can see from the figure. So at point P we will have again two fields, one is B1 and the other is B2. You can see B1 is the magnetic field due to the south pole of the bar magnet, and B2 is the magnetic field due to the north pole of the magnet. So when we consider point P at a distance r from the center O on the equatorial line of the bar magnet, now using B is equal to m naught upon 4 pi m upon r square, we use this relation. We find the magnitude of magnetic field B1 at point P due to the north pole of bar magnet is given by B1 is equal to mu naught upon 4 pi m upon np whole square. This gives us B1 is equal to mu naught upon 4 pi m upon on square plus op square. By using Pythagoras theorem, np square is equal to on square plus op square. This gives us B1 is equal to mu naught upon 4 pi m upon r square plus l square. Let us denote this equation by first. Now B1 is neither in vertical direction nor in horizontal direction. As you can see from the figure, it will have two components, one horizontal component and the other vertical component. So what is its horizontal component? Its horizontal component is B1 cos theta and its vertical component is B1 sin theta. Similarly, the magnetic field B2 at point P due to south pole of bar magnet is given by B2 is equal to mu naught upon 4 pi m upon SP square. This gives B2 is equal to mu naught upon 4 pi m upon SO square plus OP square. Again, SP square by Pythagoras theorem is equal to hypotenuse square is B square plus perpendicular square. So SP square will be equal to SO square plus OP square. So this gives us B2 is equal to mu naught upon 4 pi m upon L square plus R square. This is equation 2. So B2 is directed along PS. Now B is equal to B1 plus B2. As I told you, B1 has two components. One is along horizontal component and vertical component. So B dash I do, write it as B dash because B is the net magnetic field on the actual line of the dipole, and B dash is the net magnetic field on the equatorial line. So B dash, remember that B dash is on actual equatorial line, whereas B is on actual. So B dash will be equal to B1 cos theta plus B1 sin theta plus B2 cos theta plus B2 sin theta. But B1 sin theta and B2 sin theta are equal and opposite. So B, that is B1 sin theta is equal to minus B2 sin theta. This implies B1 sin theta plus B2 sin theta is equal to 0. This implies B dash is equal to B1 cos theta plus B2 cos theta. This implies B dash is equal to B1 plus B2 cos theta. Now we have to substitute the value of B1 and B2 from equation first and second, and we have to find the value of cos theta. So cos theta, as you can see, is equal to base by hypotenuse. This implies cos theta is equal to SO by SP, and this implies cos theta is equal to L upon under root of L square plus R square. So this will give us B. When we substitute value of B1, B2 and cos theta, we get B is equal to mu naught upon 4 pi m upon R square plus L square plus mu naught upon 4 pi m upon L square plus R square into L upon L under root of L square plus R square. This gives us B is equal to 2 mu naught m upon 4 pi L square plus R square into L upon L under root of L square, for L square plus R square is for 1 by 2. Instead of under root, we write power 1 by 2. So this will give us B is equal to 2 mu naught ml upon 4 pi L square plus R square raised power 3 by 2. Bases are same, powers are added. So in case first, it is the power is 1. Here the power is, here in this case the power is 1, and here in this case the power is 1 by 2. When you add 1 plus 1 by 2, you will get 3 by 2. That is 3 by 2. So B will be equal to 2 mu naught m into 2L divided by 4 pi L square plus R square is equal to 3 by 2. So M into 2L, as we know, that is equal to capital M, that is magnetic momentum. So B will be ultimately equal to mu naught M upon 4 pi L square plus R square is equal to 3 by 2. So when R is very very large than L, then L can be neglected, and B will be equal to mu naught M upon 4 pi R square raised to power 3 by 2. 2 and square and 2 will cancel. So we will get ultimately B dash is equal to mu naught M upon 4 pi R cube. So B is directed along PX, a line parallel to NS. Now when we compare the magnitude of the magnetic fields on action line and equatorial line, so we have to divide B by B dash, and we find that B by B dash will be ultimately equal to B into 1 by B dash, that is mu naught M upon 2 pi R cube into mu 4 pi R cube divided by mu naught M. So B by B dash will be equal to 2. This implies B is equal to twice B dash. What does it mean? It means that the magnetic field on the axial line is twice as that on the equatorial line. We have taken point P on axial line as at a distance of say 4 meters from the center on axial line, as well as on equatorial line. If it is at the same distance from on the axial line and on the equatorial line from the center of the dipole, then the magnitude of the magnetic field there will be, the net magnetic field will be on the axial line will be twice as that on the equatorial line. Thank you. See you inshallah in the next class.